We are currently in the world of inferential statistics. We started by studying descriptive statistics. Then we crossed the probability bridge. And now we're in the world of inferential statistics. So far in inferential statistics, we've studied confidence intervals. When you get a point estimate of a population parameter, we form an interval centered at that point estimate to have a better chance of that interval housing the actual population parameter. With hypothesis testing, we're going to look at claims that companies or people make about a population parameter, yet they too also don't have access to the population parameter because the population is often too large. Here is a typical example. A cell phone manufacturer says its average battery life is 24 hours. We randomly collect a sample of 50 of their phones and test their battery life. The average battery life of our sample is 23.2 hours with a standard deviation of 0.9 hours. Should we believe the company's claim? So essentially, with all of hypothesis testing, somebody's going to make a claim, and our job is to figure out whether we should believe them or not. Right? So in this case, the claim is that the average battery life is 24 hours. So if we want to do a test of this, and now the average individual wouldn't do something like this, but a company like Consumer Reports would. That's their job. They might collect a sample of 50 of these phones, a random sample, and find the average battery life of those 50 phones. And perhaps they find out that the average battery life of those 50 phones was 23.2 hours with a standard deviation of 0.9 hours. Should we believe the company's claim or not? So technically 23.2 is lower than 24, but it's not crazy. It's not like this came out to be 3.2 hours. It's 23.2 hours. And the standard deviation plays a big role in this as well. So I'm not really sure whether we should actually believe them or not. So we need to develop this mathematical process known as hypothesis testing to be able to formally say whether we should believe we are being told the truth. Hypothesis testing is a 6-step process, and here is a summary of those 6 steps. Let's just quickly go through them. We'll actually develop meaning with each of these in the coming slides. So your first step ends up being to define your pair of hypotheses. Step 2 is to note the level of significance alpha. Of course, we'll talk about that as well. Step 3, we determine the type and tail direction of the test. Step 4, we draw and label the appropriate probability distribution curve based on the type of test you're performing. This is called the critical region approach. So we're going to use the critical region approach to hypothesis testing. You could use the p-value approach. The p-value approach is very legitimate. Just the critical region approach allows us to see what's going on a little bit more easily. So we're going to do it from this perspective. If you know the p-value approach, you are more than welcome to use the p-value approach in doing problems. Step 5, we compute our test statistic, then make a conclusion about H naught. And then finally, step 6 is to make a conclusion about the claim and interpret our results. Let's now take a deep dive into each of these steps so we can see how the hypothesis testing works. Step 1 is to define our pair of hypotheses. So whenever we're doing hypothesis testing, we have 2 hypotheses. One is called the null hypothesis and one is called the alternative hypothesis. The null hypothesis, the notation used for that is H sub 0. You'll often hear me say H naught. People in England refer to 0 as naught. So this is H naught, and the alternative hypothesis is referred to as H sub A. It also could be referred to as H sub 1, but in our case, we're going to refer to it as H sub A. The key thing about these 2 hypotheses is that they must be complements of one another. So we talked about complementary events when we studied probability. So let's run through an example here. Write the complement of each of the following events. So what is the complement of it's raining outside? Some people might say that it's sunny, and that's not correct because technically it can rain and be sunny at the same time, and it could not be raining and not be sunny. So it's got to be literally every other scenario except for when it's raining. So the only way you can sum that up is to say it's not raining. So the complement of raining is it's not raining. The complement of at least 10, well, you could adopt the same sort of idea here and say it's not at least 10, but we want to be more articulate than that. If it's not at least 10 means 10 or more. That means it's less than 10 is the complement. The complement of more than 10 is not less than 10 because 10 is not part of more than 10. 10 is not part of less than 10. So more than 10's complement is less than or equal to 10. So we can't leave out the equal part. So less than or equal to 10. Remember, the complement does not overlap at all with the original event, but it covers all of the other possibilities as well. And the complement of not 10 is that it is 10. We are going to start by doing hypothesis testing on the mean, and specifically one sample testing on the mean. And so we're going to be dealing with scenarios like this when it comes to hypothesis testing, because somebody's going to make a claim about the mean, that the mean is less than 10, or that it's greater than or equal to 30. These are the types of things we're going to be dealing with. So let's formalize this in the next slide. We will start by doing hypothesis testing on the mean. So there are 6 possible statements that can be made about the mean. K is a specific number, and of course, mu is our variable that represents the population mean. So someone can say that mu is less than K, mu is less than or equal to K, mu is greater than K, mu is greater than or equal to K, mu is K, or mu is not K. We need to know the complements of each of these 6 events because the null hypothesis and the alternative hypothesis have to be complements of one another. So if you have mu is less than K, the complement of that is not that mu is greater than K. That leaves out specifically K. So the complement of mu is less than K is that mu is greater than or equal to K. And the complement that mu is less than or equal to K is that mu is greater than K. This one over here has the equality this time. The complement of mu is greater than K is mu is less than or equal to K. Can't leave out the equality. Mu is greater than or equal to K. Its complement is mu is less than K. Everything else. The complement of mu equals K is that mu is not equal to K. And the complement of mu is not equal to K is that mu does equal K. A claim about a mean can be represented in any one of these 6 ways, and then these are the corresponding complements of each of those 6 ways. Let's now apply this to the original cell phone battery life problem that we looked at to start. Recall, a cell phone manufacturer says its average battery life is 24 hours. We randomly collect a sample of 50 of their phones and test their battery life. The average battery life of our sample is 23.2 hours, with a standard deviation of 0.9 hours. Should we believe the company's claim? All right, so they are making a claim about the battery life that involves this 24 hours. So they're saying that mu is 24 hours. So mu is the population mean, but when it comes to hypothesis testing, we often call it the hypothesized mean because they didn't actually test all the batteries. So they don't actually know exactly what mu is, but this is their claim about mu. So first, write down the claim and actually mark that it's the claim. So their claim is that mu is equal to 24. And again, that is the claim. I am not going to worry about what's the null hypothesis and what's the alternative hypothesis until I have both hypotheses down. So we have the claim hypothesis. Now we need the complementary hypothesis. The complement of mu equals 24 is mu is not equal to 24. Once you've got both complementary hypotheses down, then we assign one to be the null hypothesis and one to be the alternative hypothesis. Now you do not choose this at random. This is the key thing right here. The null hypothesis is the one that contains the equality. Ultimately, the testing is done on the null hypothesis. And in particular, you're technically starting out by assuming that H naught is true. However, we are not going to go into the theoretical aspects of how hypothesis testing is done. We're primarily going to be going through the procedural aspects of it. So if you want to have a more theoretical or conceptual understanding of this, I highly recommend you read the book and some other resources. We are going to work on developing a procedural understanding of hypothesis testing. So the key thing to remember is that the null hypothesis is always the one that contains the equality. Here we have the equality, so this is our null hypothesis. Now I want to point out something that you should be aware of. In this case, the claim is the null hypothesis. That is not always true. Sometimes students assume that the null hypothesis is the claim. It just so happens that in this case, the null hypothesis is the claim. In other examples, you'll see the claim may be the alternative hypothesis. So beware of that. Now that we've got step 1 down, we move on to step 2, where we make note of the alpha level. But before we make note of the alpha level, what does that actually mean?